not a single eruption, not an isolated event. A continuous, rapid-fire sequence of coronal mass ejections departing the solar disk from the same active region 4479, over a period of days. More than 5 solar storms racing toward Earth simultaneously, the first arriving before noon UTC on July 3rd, the subsequent impacts following in stages through July 6th. A G2 moderate. Geomagnetic stormwatch from NOAA's Space Weather Prediction Center. Aurora visible as far south as New York, Wisconsin, and Washington State. 10 solar flares in a single 24-hour period from the same region. That was 3 weeks ago, and the sun has not stopped. As of July 23, 2026, NOAA's Space Weather Prediction Center is forecasting that CMEs that left the sun on July 20th and 21st may deliver glancing blows to Earth's magnetosphere, with G1 minor geomagnetic storm conditions possible on July 24th and July 25th. Conditions may gradually ease as the coronal hole stream wanes by July 25th. 3 separate solar disturbances arriving at Earth this week, the first and second from CMEs that left the sun's surface on July the 20th and 21st, respectively. The third from a coronal hole high-speed stream, a separate, completely different solar phenomenon that is simultaneously funneling accelerated solar wind into Earth's magnetosphere from a different source entirely. 3 separate mechanisms, 3 separate arrival windows, all converging on Earth's magnetic field in a single week that NOAA's own forecast describes as progressing from unsettled through active to G1 storm conditions across 4 consecutive days. This is not the quiet week the monthly calendar might have suggested at the start of July. It is the latest chapter in a solar activity story that has been unfolding since the sun crossed the threshold into solar cycle 25 maximum, a maximum that has produced more X-class flares, more CMEs, more geomagnetic storm activity, and more aurora, sightings at mid-latitudes than any comparable period since the early 2000s. To understand what 3 compounding solar storm arrivals this week actually mean, for power grids, for GPS, for satellite operations, for radio communications, for anyone who wants to see the northern lights, you need to understand the architecture of what is hitting Earth, and why the specific combination of a CME impact and a coronal hole high-speed stream arriving simultaneously produces conditions different from either one arriving alone. Start with the CMEs from July 20th and 21st, because these are the component of this week's solar activity that NOAA is tracking most actively right now. A coronal mass ejection is a cloud of magnetized plasma expelled from the sun's corona. The corona, the sun's outer atmosphere, visible during solar eclipses as the pearly white halo surrounding the disk, is threaded with magnetic field lines that, under the right conditions, can become unstable. When a magnetic configuration in the corona reaches a threshold of complexity and energy, the field lines can snap and reconnect in a process called magnetic reconnection that suddenly releases enormous amounts of stored magnetic energy. Some of that energy goes into accelerating electrons to near-light speed, producing the X-ray burst we detect on Earth as a solar flare. Some of it goes into ejecting a bubble of plasma and magnetic field outward from the corona at speeds that can range from a few hundred to several thousand kilometers per second. The CME from July the 20th and the CME from July 21st were produced by active regions that NOAA has been monitoring as ongoing flare risk zones throughout July. The forecast indicates glancing blows from these CMEs on July 24th and 25th with unsettled to active conditions and G1 storm potential across both days. The word glancing in a NOAA forecast carries a specific technical meaning that matters for understanding the impact level. A glancing blow describes a CME that passes near Earth but does not make a direct hit. The plasma cloud's center is offset from Earth's position, meaning the leading edge of the CME clips Earth's magnetosphere on one side rather than impacting it head-on. Full halo CMEs, the type where the ejection appears as a complete ring expanding around the solar disk as seen from Earth, indicating the eruption is directed almost directly at us, produce the most severe geomagnetic storms because they deliver maximum plasma and magnetic flux into Earth's magnetosphere. Glancing blows from partially Earth-directed CMEs produce more moderate conditions, typically G1 to G2 on NOAA's 5-level geomagnetic storm scale, but they are not trivial. Even a glancing G1 storm can produce aurora at mid-latitudes, disrupt high-frequency radio communications at high latitudes, cause minor power grid voltage fluctuations, and increase satellite drag in low Earth orbit in ways that require operational adjustments from satellite operators. But here is where the July 24th to 25th window becomes more complex than a simple CME glancing blow. Simultaneously with the CME arrivals, a coronal hole high-speed stream is interacting with Earth's magnetic environment. A coronal hole high-speed stream is contributing to the unsettled conditions through this period. Coronal holes are regions of the sun's corona where the magnetic field is open. The field, Lines extend outward into space rather than looping back to the solar surface. Because the magnetic field is open, solar wind plasma in these regions is not trapped and can accelerate to higher velocities than the typical ambient solar wind. A coronal whole high speed stream is the sustained jet of fast solar wind that flows from this open region and sweeps across the solar system in a rotating beam synchronized with the sun's 27-day rotation period. When one of these beams sweeps across Earth's position, it compresses the magnetosphere and can produce extended periods of geomagnetic activity that last days rather than hours. The combination of a CME impact and a coronal whole high-speed stream arriving in the same narrow window is what forecasters describe as a compound geomagnetic event. The CME provides an initial shock, a sudden compression of the magnetosphere, followed by enhanced plasma and magnetic flux. The coronal whole stream then sustains the disturbed conditions after the CME's initial push passes. The result can be a geomagnetic disturbance that lasts significantly longer than either source would produce in isolation. Now, the storm levels and what they actually mean for people who are not solar physicists. NOAA uses a 5-level scale for geomagnetic storms, designated G1 through G5. G1 is minor. G5 is extreme, the category that produces storm currents capable of knocking out power grids across entire regions. This happened on March 13, 1989, when a G5 storm caused a 9-hour blackout for the entire province of Quebec by inducing currents in the Hydro-Quebec power grid that the system was not designed to handle. The current forecast for July 24th and 25th is G1, the lowest storm level. But G1 does not mean inconsequential. Potential impacts at G1, G2 storm levels include possible power grid fluctuations and voltage alarms in high-latitude systems, satellite orientation irregularities, increased drag on low Earth orbit satellites, fading of high-frequency radio propagation at high latitudes, and aurora visibility as far south as New York, Wisconsin, and Washington State. Each of those impacts deserves individual attention because they affect different populations in different ways. Power grid fluctuations at G1 to G2 levels are not the catastrophic outages associated with extreme storms. They are voltage fluctuations that protection systems in modern high-latitude grids are designed to handle. Grid operators in northern Canada, Scandinavia, northern Russia, and Alaska monitor geomagnetic activity indices in real time and have procedures for adjusting generation and switching operations when storm indices rise above thresholds. The concern is not that a G1 storm will knock out the grid. It will not, under normal circumstances. The concern is that a G1 storm arriving on top of existing grid stress, during a heat wave, for example, when power demand is already at peak, reduces the margin for error that grid operators depend on. Satellite orientation irregularities at G1 to G2 levels reflect the effect of enhanced solar wind pressure on the ionosphere and upper atmosphere, which increases the density of the atmosphere at low Earth orbit altitudes. That increased density produces more drag on satellites, which gradually lowers their orbits faster than nominal predictions allow for. Operators of low Earth orbit constellations, including Starlink, which currently operates more than 7,000 satellites in the altitude range most affected by geomagnetic storm-induced atmospheric drag, must monitor this effect and adjust station-keeping fuel usage. During the G5 storm of May 2024, Starlink's own engineers described the challenge of managing enhanced drag for their entire constellation simultaneously. High-frequency radio propagation effects at G1 to G2 levels affect aviation and maritime communication at high latitudes, where HF radio is still the primary over-the-horizon communication channel for aircraft crossing the polar routes between North America and Asia. When a geomagnetic storm increases ionospheric absorption of radio waves at polar latitudes, pilots and air traffic control centers lose reliable HF communication and must use alternative channels. This is not a safety catastrophe. Polar route flights have procedures for handling communication disruptions, but it adds complexity to one of the world's busiest long-haul aviation corridors. GPS effects at G1 to G2 levels operate through a different mechanism. The ionosphere refracts radio signals passing through it, and the degree of refraction depends on the ionosphere's electron density. Under geomagnetic storm conditions, the ionosphere becomes denser and more variable, and the electron density variations introduce timing errors into GPS signals that receivers on the ground use to calculate position. At G1 levels, this effect typically produces positioning errors of 1 to several meters for standard GPS receivers, undetectable for most navigation uses, but potentially significant for precision agriculture, construction surveying, and aviation instrument approaches that depend on GPS accuracy measured in centimeters. Now, aurora, because this is what most people want to know about when a solar storm forecast is issued, and because the conditions this week are genuinely producing an opportunity, aurora visibility as far south as New York, Wisconsin, and Washington state was forecast for the G2 storm conditions during the early July sequence. The G1 conditions, expected July the 24th to 25th, pushed the aurora oval equatorward to approximately 55 degrees geomagnetic latitude, roughly the level of the US-Canada border at the longitudes of the Great Lakes. At G1 levels, the northern lights are primarily visible from Canada, Alaska, Scandinavia, Scotland, and the northern fringe of the continental United States. During the storm's brief peaks, the moments when the KP index reaches 5 or briefly touches 6, the aurora oval expands further south, and observers in the northern tier of U.S. states may see the aurora on the northern horizon, typically as a greenish or sometimes reddish glow, rather than the overhead curtains that observers at higher latitudes experience. The best conditions are after local midnight, away from city lights with clear skies and a northward-facing horizon with no obstructions. And most critically, the aurora's appearance during any geomagnetic storm is not guaranteed. A forecast of G1 conditions is a forecast of the geomagnetic disturbance level. Whether the aurora is visually impressive depends on the specific orientation of the incoming CME's magnetic field, specifically whether the field's BZ component is strongly southward, which allows the magnetosphere to couple efficiently with the CME and produce maximum energy deposition into the polar atmosphere. Now, the context that explains why 3 solar storms in a single week in late July 2026 is not a statistical anomaly. It is a consequence of where we are in the solar cycle. The Sun operates on an approximately 11-year cycle of activity, alternating between solar minimum, the quiet period when sunspot numbers are low, flares are rare, and the solar wind is relatively steady, and solar maximum, when the Sun's magnetic field is at its most complex and dynamic, sunspot numbers peak, and X-class flares and major CME events become commonplace. Solar cycle 25 crossed into its maximum phase in late 2024 and is expected to remain at peak activity levels through at least mid-2026. Some forecasts extend the maximum influence into 2027. Active region 4479, which produced the X1.1 flare and full halo CME on June 30th, 2026 that launched the machine gun sun sequence, was identified by NOAA as a continuing flare risk region through early July. In addition, recurrent coronal hole high-speed streams can return roughly every solar rotation, approximately 27 days, and briefly disturb Earth's magnetic field even when no dramatic solar flare is visible. That 27-day recurrence is significant. The same coronal hole that produced the high-speed stream currently interacting with Earth's magnetosphere this week will rotate back around to the Earth-facing side of the Sun in approximately 27 days. If it remains open, which coronal holes frequently do across multiple solar rotations, the same high-speed stream will arrive again in late August, on schedule, producing another period of enhanced geomagnetic activity. This is not speculation. It is the predictable geometry of the Sun's rotation applied to the known behavior of coronal holes. The accumulating frequency of these events through solar cycle 25 maximum is what scientists are watching most carefully in the context of what happens next. Not any single CME, not any single storm. The pattern. Space weather physicist Dr. Tamitha Skov noted that multiple Earth-directed CMEs in rapid sequence are consistent with a solar active region of high complexity, and that X-flare risk remains elevated over extended windows as such regions cross the Earth-facing disk. The answer to the question of what happens next involves 2 timescales. In the immediate term, July 24th to 25th, the CMEs from July 20th and 21st arrive, interact with the existing coronal hole stream, and produce G1 conditions across a window of approximately 48 hours. Power grid operators at high latitudes are monitoring, satellite. Operators are tracking drag rates. Aurora watchers across the northern US and Canad AA are checking KP forecasts. HF radio operators at high latitudes are preparing for possible propagation disruptions. None of that is alarming. All of it is the operational reality of living through a solar maximum, and all of it is being managed by the agencies and operators that exist specifically for this purpose. In the medium term, the remainder of solar cycle 25 maximum through 2026, the cadence of activity that produced the machine gun sun in early July, the G1 watches for late July, and the ongoing flare. Risk from active regions crossing the Earth-facing disk is expected to continue. Solar maximum does not produce uniform activity. It produces clusters of high activity separated by quieter intervals, with the overall frequency of significant events. M-class and X-class flares, Earth-directed CMEs, major geomagnetic storms, substantially higher than at solar minimum. The number of named geomagnetic storms NOAA has formally tracked in 2025 and 2026 is already well above the comparable period of the previous cycle. And in the background of all of it sits a question that connects this week's three-storm sequence to the longer-term scientific conversation. What does sustained solar maximum activity do to the accumulated effects on Earth's technological infrastructure? Every G1 and G2 storm that passes through the magnetosphere deposits heat into the upper atmosphere, accelerates the orbital decay of low Earth orbit satellites, induces small currents in power grid infrastructure, and degrades the accuracy of GPS positioning systems for hours to days. Each individual event is manageable. The concern that power grid engineers and satellite operators raise, and that the U.S. government's NOAA Space Weather Action Plan and the equivalent European framework are specifically designed to address, is the cumulative effect of many moderate events over a sustained maximum combined with the statistical certainty that at least one major extreme event will occur before the cycle ends. The last G5 extreme geomagnetic storm, the Carrington-level event benchmark that infrastructure planners use for worst-case planning, occurred in May 2024. The Carrington event itself in 1859 was a G5 storm estimated to have been 3 to 4 times more powerful than May 2024's event. If a Carrington-equivalent storm hit Earth today, the consequences for modern infrastructure, which has orders of magnitude more vulnerability through its satellite dependence, GPS reliance, and grid interconnection than any infrastructure that existed in 1859, would be categorically different from what any previous extreme storm has produced. That scenario is not forecast for this week. The G1 conditions on July the 24th and 25th are at the low end of the storm scale. But the frequency of activity that is producing 3 storm weeks like this one is exactly what keeps space weather scientists watching the sun carefully, because the next event on the calendar after 3 G1 glancing blows could be a direct hit X-class CME from a complex active region at the height of solar maximum. And between those two events, the difference in ground level impact is not linear, it is exponential. NOAA's Space Weather Prediction Center issues updated space weather forecasts every 3 hours. The current watch for G1 conditions, July 24th and 25th, will be updated as the CMEs approach and real-time magnetometer data from the ACE and DSC-OVR satellites, positioned at the L1 Lagrange point between Earth and the Sun, begins to measure the actual magnetic field strength and orientation of the arriving plasma. The most critical measurement is the BZ component, the north-south orientation of the CME's magnetic field. Southward by Z means the CME's field connects efficiently to Earth's field and deposits maximum energy. Northward BZ means limited coupling, and a weaker storm than the forecast suggested. That measurement only becomes available roughly 30 to 60 minutes before the CME arrives at Earth, which is why the community watches and waits through these arrival windows with the specific focus of people who know the answer is coming but have not received it yet. This week's 3 storms are manageable. The sun at maximum is always managed. What scientists are watching most carefully as this week's triple hit unfolds is not any single storm's impact. It is what the pattern of 2026's solar activity reveals about where solar cycle 25 is heading in the months that remain before the maximum transitions to its declining phase. Every major active region that crosses the Earth-facing disk is an opportunity to refine the prediction of how active and how dangerous the remaining maximum will be. 3 storms this week is a data point in a sequence that is still being written by a star that does not consult the forecast calendar before deciding what to do next. Subscribe right now and turn on the notification bell. NOAA SWPC updates its space weather forecast every 3 hours. The CME arrivals on July 24th and 25th will be measured in real time by DSCOVR and ACE. When the BZ measurements come in and the actual storm level verifies or exceeds the G1 forecast, this channel will have the update before it reaches anywhere else.